Welcome to the video lecture of Electronic Devices KEC 301. The unit discussed will be Unit 4. The topic is bipolar junction transistor. In the previous videos, we have seen about the different configurations of bipolar junction transistor, that is how it behaves with the biasing in common base configuration and its structure, terminals, that all we have discussed. And we had also discussed the common emitter configuration. So in continuation with the common emitter configuration of bipolar junction transistor, I will be discussing in same continuation in this video. Beta, that is amplification factor that we define for common emitter configuration. So in the DC model, the level of IC and IB are related by a quantity called beta and defined by the equation beta DC as IC upon IB, where IC and IB are determined at a particular operating point on the characteristics. For practical devices, the level of beta typically ranges from about 50 to over 400 value, with most in the mid-range. As for alpha, beta certainly reveals the relative magnitude of one current to the other. For a device with a beta of 200, the collector current is 200 times the magnitude of that of the collector current. For a device which has a beta 200, the collector current is 200 times the magnitude of the base current. On a specification sheet, beta DC is usually included as HFE with the H derived from an AC hybrid equivalent circuit. So that is H parameter. The subscript FE are derived from forward current amplification and common emitter configuration respectively. Means HFE is forward current amplification for common emitter configuration. For AC situations, and AC beta has been defined as beta AC is the ratio of output change in the output current with the change in the input current for a constant value of output voltage. That is beta AC, we have delta IC upon delta IB for a constant value of VCE. The formal name for beta AC is common emitter voltage, that is forward current amplification factor. Since the collector current is usually the output current for a common emitter configuration and the base current the input current. The formal beta AC is common emitter forward current amplification factor since the collector current is usually the output current for a common emitter configuration and the base current the input current. The term amplification is included in the nomenclature, that is HFE, and the equation, that is beta AC is equal to delta IC by delta IB for constant value of VCE is similar in format to the equation for alpha AC that we have seen previously for the common base configuration. The procedure for obtaining alpha AC from the characteristics curve that we can also use because of the but we are not discussing here due to its difficulty of actually measuring the current IC and IE on the characteristics. The equation, that is beta AC is equal to delta IC upon IB, however, is one that can be described with some clarity, and in fact the result can be used to find alpha AC using an equation to be derived that we will see. On a specification sheet, beta AC is normally referred to as HFE. Note that only difference between the notation used for the beta, that DC beta, specifically beta DC is equal to HFE, is the type of lettering for each subscript quantity. The lowercase letter h continues to refer to the hybrid equivalent circuit, that is hybrid equivalent parameters of the circuit. Beta that we can calculate from the characteristics. This is the characteristics that is plotted between VCE and IC, that is output voltage and the output current, and the varying curves are for the different values of the input current IB. So if we want to determine this beta from the graph, then we have beta AC. So we need to have delta IC upon delta IB. So delta IC is this change in value for constant value of VCE of 7.5 volts. So corresponding to this 7.5 volts, we have 2 points on the IB curve. Corresponding to these 2 points, we have the collector current values IC1 and IC2. So difference of this IC1 and IC2 will give delta IC. And from the difference of IB1 and IB2, we get 30 microampere minus 20 microampere, that is delta IB. So 1 milliampere divided by 10 microampere for a constant value of VCE of 7.5 volts. We get beta AC at 100. To calculate beta DC, we have a Q point value for which we have IC and IB value. Corresponding IC value is 2.7 milliampere and corresponding IB value, that is base current, is 25 microampere for a constant VCE value 7.5 volts. So this beta AC comes out to be 108. So both beta values are usually reasonably close and are often used interchangeably. Now we have studied about the amplification factor, that is alpha for common base configuration and beta for common emitter configuration. Now we will see that how we can establish a relationship between alpha and beta. A relationship can be developed between beta and alpha using the basic relationship that we have seen. Using the beta is equal to IC by IB, we have IB is equal to IC by beta, and from alpha we have IC upon IE. So we can write IE is equal to IC upon alpha. And the current equation using the Kirchhoff current law we have written as IE is equal to IC plus IB. So substituting the value of IE as IC upon alpha and IB as IC upon beta and dividing both sides of the equation by IC, we get the value 1 upon alpha is equal to 1 plus 1 upon beta. So simplifying this, we get beta is equal to alpha multiplied by beta plus alpha. Taking alpha common from these two terms, we get beta plus 1 multiplied by alpha. So simplifying this, keeping alpha on left hand side, we get alpha is equal to beta upon beta plus 1. And further we can get beta in terms of alpha as beta is equal to alpha upon 1 minus alpha. Although we have relationship between alpha and the current and beta and the current, these two relationships are also very important so that we can relate a common base configuration parameters with a common emitter configuration parameters. In addition, recall that we had equation ICEO is equal to ICBO divided by 1 minus alpha. By using an equivalence of 1 upon 1 minus alpha is equal to beta plus 1, derived from the above, we can find IEO is equal to beta plus 1 multiplied by ICBO. We can write this as ICEO nearly equal to beta ICBO by ignoring this 1 due to the high value of beta as compared to 1. We have seen that the beta value ranges between 50 to 400. So we have ignored 1 with relation to the higher value of beta. So we can write ICEO is equal to beta ICBO. Biasing of common emitter configuration. This is a common emitter configuration. This terminal is base, this is collector, and this is emitter. Now there are two question marks placed to show that how we can bias a common emitter configuration for its proper working. So the diagram B, that is representing the direction of flow of current. So I have made here the current IE is outwards, current IC and IB are flowing inwards into the terminal. Now biasing this system for the proper operation, we have, this is an NPN transistor. So base is of P type, emitter is of N type. So we have a battery connected here. Base is connected to the positive, emitter is connected to the negative. So this input side is now forward bias. And the output, that is collector side, we need to keep it reverse bias if we want to operate the device in active mode. So this has been reverse bias. So this biasing configuration is done for the proper operation of the common emitter configuration into active mode of operation. And as we increase the reverse voltage, this active mode operation will reach to a saturation level value. The third configuration of bipolar junction transistor is common collector configuration. Till now we have seen common base configuration and a parameter, a term related to it was alpha. Then second we had the common emitter configuration with an amplification factor that was represented by beta. Now we have the third, that is common collector configuration. In the common collector configuration, the collector terminal will be common between the remaining two terminals. The remaining two terminals are the base and the emitter. So we need to design a connector circuit in such a way that the collector is common between the base and the emitter. So now in the diagram figure A, we can see that the terminal collector, that is common between the base B and the emitter E. A battery VBB is connected between the base B and collector C, and another battery is connected between emitter E and the collector terminal C. The lower one is the symbolic representation of bipolar junction transistor. So this diagram, we can see the base terminal, that is of N type, is connected to the negative of the battery, and the collector terminal is of P type and connected to the positive of the battery. Similarly, if we see this NPN transistor, then in this the collector terminal is made common. Base being of P type is connected to the positive terminal of the battery, and collector, that is connected to the negative terminal of the battery, making the input side junction forward biased. And if we look towards the output side junction, then emitter terminal, that is of N type, is connected to the negative terminal of the battery, and in that way it is made, the output junction is made forward biased. The lower one is the symbolic representation of that bipolar junction transistor, and it is showing the direction of current. IE current is outward, IB current is inward, and IC current is inwards. So in this case also, for the common emitter configuration, common collector configuration, we can write the current equation as IE is equal to IC plus IB. So this I also told you earlier that the current IE is equal to IC plus IB. This equation will be valid for all the three configurations: common emitter, common base, and common collector. A common collector circuit configuration provided in the figure with the load resistance connected from emitter to ground. Note that collector is tied to the ground even though the transistor is connected in a manner similar to common emitter configuration. From a design viewpoint, there is no need for a set of common collector characteristics to choose the parameter of the circuit of the figure. It can be designed using common emitter characteristics of the common collector configurations are same as for the common emitter configuration. For the common collector configuration, the output characteristics are a plot of IE versus VCE for a range of values of IB. The input current therefore is the same for both common emitter and common collector characteristics. The horizontal voltage axis for the common collector configuration is obtained by simply changing the sign of the collector to emitter voltage of a common emitter characteristics. Finally, there is an almost unnoticeable change in the vertical scale of IC of the common emitter characteristics if IC is replaced by IE for the common collector characteristics, since alpha is nearly equal to 1. For the input circuit of the common collector configuration, the common emitter base characteristics are sufficient for obtaining the required input ground terminal. This diagram is showing the common collector configuration characteristics. The characteristics are similar to those of the common emitter configuration, except the vertical axis is IE. Power dissipation of the three configurations can be defined in terms of voltage and current. If we talk about common base configuration, then maximum power consumed for a common base configuration is VCB multiplied by IC. For common emitter configuration, we have VCE multiplied by IC. Then the third one, common collector configuration, the power consumption maximum value can be calculated by obtaining a product of VCE multiplied by IC. In this way, using the output current and the output voltage, we can calculate the power dissipation of the three configurations of the bipolar junction transistor. Now we have different BJT device models. The primary function of a model is to predict the behavior of a device in particular operating regions. We have a small signal model and large signal model. Under the small signal model, we have hybrid 8 parameter model and hybrid pi models. Large signals model, we have Ebers-Moore model and Guillemot model. In Ebers-Moore model, we have voltage and current control models. What is Ebers-Moore model? The classic mathematical model for the bipolar transistor is Ebers-Moore model that was formulated by J. Ebers and J. L. Knoll from Bell Laboratories in early 1954. Ebers-Moore model, also known as coupled diode model. The Ebers-Moore model provided an alternative view or representation of the voltage current equation model. Model includes configurationally series resistance, depletion capacitance, and charge carrier effects. Ebers-Moore model designing. Ebers-Moore model for PNP transistor involves two ideal diodes packed back to back with the saturation current. IEO and ICO are the two current-dependent control sources shunting the ideal diode. So the two diagrams are represented here. The first one is the transistor current and voltage direction representation, and the second one is the Ebers-Moore model of the PNP transistor. In the first diagram, that is transistor currents and voltage direction, in that we can see there is a emitter current IE and flowing into the emitter junction. Across this emitter and base voltage, we have voltage VB, and between the base and collector we have voltage VC. The voltage between the emitter terminal and the collector terminal is represented as voltage VCE. A resistance here is represented RBB dash, through which the current IB is flowing. The voltage between collector and base is VCB, and the voltage between emitter to base is VE. So if we look into the Ebers-Moore model of PNP transistor, here we have terminal, this is emitter terminal, the center one is the base terminal, and on the right hand side we have collector terminal. Between this emitter and base there is one diode connected, and minus IEO current is represented here. On the output side, we have a diode in opposite direction connected because we are doing it for PNP transistor. So first diode will be P and N in this way connected, and the second will be in reverse. That is from N to P connection. Here it is. The voltage across the first input side diode is VE, and for the second one it is VC. The current source that is represented here is alpha I IC, and on the output side we have alpha N IE. So this is the Ebers-Moore model representation of the PNP transistor. Different equations associated with the Ebers-Moore model that we can write by applying KCL to the emitter node. We get IE is equal to alpha I, IC is equal to I. We have IE is equal to I minus alpha I, IC, or we can write IE is equal to minus alpha I, IC plus I. Simplifying, we can write IE is equal to minus alpha I, IC plus I naught EVE divided by VT minus 1. IE can be written as minus alpha 1 IC minus IEO EVE divided by VT minus 1. This model is valid for both forward and reverse static voltages applied across the transistor junction. So the current IE, here is the emitter current, V is the voltage across the emitter, VT is the threshold voltage. In the above model, by making the base width much larger than the diffusion length of the minority carriers in the base, all minority carriers will recombine in the base and none will survive to reach to the collector. So this model is of this is very important. We have seen that we are having different models also, H parameters model, large signal model and small signal model. So till now we have studied about the basics of bipolar junction transistor, its terminal, how we can bias a bipolar junction transistor, its different configuration, common emitter, common base and common collector configuration. And we also have discussed about the characteristics of all the three configuration, and we have seen that the most widely used configuration out of these three configurations of bipolar junction transistor is the common emitter configuration.